Okay, welcome back everybody. So we'll start this next session. So we're going to start with Urna Basu from the SM Bose National Center for Basic Sciences in Kolkata. And she's going to talk to us about attractively coupled active particles, emergent short-range repulsion. So I'll start the timer.
So I'd like to start by thanking the organizers for giving me the opportunity to speak here. This talk will be based on a joint work with the PhD student who is working with me. We have already heard a little bit about active motion in this conference in the last 2 days. So I'll just give a very brief introduction. So active motion refers to kind of a persistent motion performed by self-propelled particles. Self-propelled particles like bacteria or birds, which we observe in nature. And there are also many artificial entities which are designed in lab nowadays, like genus particles or various kinds of micro and nano swimmers. So the specialty about this motion is that they break detail balance at a very microscopic level, at individual level, and they consume energy from environment to convert it to a directed motion. So because of this very non-equilibrium nature of their motion, they show a lot of novel emergent behavior at the collective level. For example, flocking, swimming, motility-induced phase separation, various kinds of pattern formation. So here are some examples from some experiments. So here's a living crystal, dynamic crystal formation, motility-induced phase separation, bacterial colony growth, and trapping. This experiment is done in ISC. Sriram was here. He's a part of it. It's done in Ajay Sood's lab. So the key feature in many of these phenomena are the tendency of these particles to cluster together, even in the absence of any attractive interaction. Okay, so somehow they generate an effective and attractive interaction. And to understand this kind of emergent interaction from a microscopic picture, the starting step would be to take just two particles, and see how this attractive interaction emerges. So this has been done in some example systems over the last 10-12 years. This was first done by Martin Evans and group in the context of two random thermal particles moving on lattice, and they showed that in presence of this exclusion interaction, an attractive interaction emerges. Okay. Later, this was studied also in various other settings by Anupam, Abhishek, Shotto, Gregory, and other people, who showed that in various different contexts, in presence of repulsion, in presence of attractive coupling, in presence of finite tumble duration, a general picture emerges, which is that these particles tend to attract each other. So there is an emergent attractive interaction. Okay. So the question we are going to ask here today is that, is it true that they always attract each other, or is it possible that the active particles also repel in some context? And the answer is yes, and somewhat counterintuitively, it turns out that they can repel each other when they are very strongly attractively coupled. Okay. So this is going to be the outline of the talk. So I will introduce the coupled active Brownian particle model, and I'll talk about the two particle case where we can have an explicit exact solution for at least harmonic coupling, and then I'll go to more general coupling strength and many particle, general coupling function and many particle cases. Okay, so here is the setup. We have n active Brownian particles, and the positions are Ri, and they are, each pair is coupled by some attractive potential Vr, which is rotationally symmetric. It depends only on the distance between the two particles. So the Lanzwa equation for the ith particle is this. So this is the force coming from all the other particles which are coupled to this particle, and this is the self-propulsion term. So the speed is Vi, and Ni is a unit vector. So the angle theta I characterizes this unit vector, and this angle undergoes a rotational diffusion. So it's a usual active Brownian motion. Only thing is that each of the particle has their own self-propulsion speed. So let's first look at what happens in this case. So these are scenarios in 2 and 3 particle cases. Here the particles are coupled via quartic coupling, and so what we see is that each pair kind of maintains a social distance, so they don't go very close to each other. So had they been passive particles, they would most likely have been I mean, r equal to 0 would be the most likely configuration. So this is, okay, I forgot to mention, this is in the center of mass frame. So this center is the center of mass of the 2 particles and 3 particles here. So we see something a bit unusual emerging here. So this repulsion, so the particles maintain a minimum separation. So that's like a repulsive effect, and that emerges from this strongly attractively coupled system. Okay, so let's now try to understand what, how we can understand this thing. So let's first take the simplest scenario. So 2 particles coupled harmonically. So this is my potential, and we look at the evolution of the relative coordinate. The center of mass, of course, evolves freely like an active particle, but we look at the separation degree. So if we look at the separation degree, the Langevin equation is this. So we have the attraction term. So this is like a single particle moving in a trap of strength 2K. And then there is a noise. The noise is a combination of the 2 noises coming from the 2 particles, and it's a bit different, and that's what makes all the difference. So formally we can solve that equation. This is the solution. But what we want to look at is the strong coupling regime. So strong coupling regime meaning when the coupling strength is very large compared to this diffusion coefficients D1 and D2. So in this case there is kind of a time scale separation. So the particle, I mean this R, relaxes in the trap much faster before the theta I, theta 1, theta 2 evolve appreciably. Okay, so in this, under this approximation, the distribution of R we can find as this. So we let the particle let R relax for a given theta 1, theta 2, and then average over all possible values of theta 1, theta 2. Okay, so this is very simply the distribution for a given theta 1, theta 2. Then we have to just average over this. So what first we, I mean, if we look at the distance, what it does, so for a fixed theta 1, theta 2, it just goes to a fixed point, right? It's a completely deterministic dynamics. Sorry, completely deterministic dynamics. So it goes to a point which is given by this. So for a fixed theta 1, theta 2, the distance goes to this value. And what we need to look at is what is the minimum and maximum value of this possible R. Since cos is a bounded function, it can go between -1 and +1. So it turns out this R is actually bounded in this regime. So there is a minimum value which is nothing but the, proportional to the difference of the 2 speeds. So as long as the speeds of the particles are different, they cannot come very close to each other. So there is like a repulsive effect. The maximum is also bounded by the speeds V1 plus V2. And it also happens that this minimum separation is approached when the particles, their orientations are parallel to each other. On the other hand, the maximum is approached when their orientations are anti-parallel, so when they are moving head on. So this maximum displacement in a trap is quite common for any active particle moving in a trap, strong enough trap, it cannot go farther than a particular point. But this emergence of this minimum point, so the distance must maintain a minimum value, that is something new, that's coming purely because of the self-propulsion speed and also of course because of the strong coupling regime that we have assumed. Okay. So what happens physically is that when so this was our equation. So when R is smaller than this distance, then there is always an effective push due to the difference of the self-propulsion speeds, and that effective push generates the repulsive effect. So let's now try to understand this a bit more analytically. So we can actually find the distribution of the separation exactly, and it turns out that it has a scaling form like this. R max is this V1 plus V2 by K, and the scaling function can also be calculated exactly. So this is a comparison where we compare with numerical simulations done with a small value of D, but the result does not depend on the actual value of D as long as D is much smaller than K, and that's what we also see in simulation. And this is, so the particles are most likely to be either at this point of nearest approach or at the point of furthest approach, at least for the harmonic coupling. So we can also calculate the X marginal distribution exactly. This also has a similar scaling form, but the scaling function is a little bit different. And the scaling function has 2 peaks. So this is X by R max. So the peak, so there is a minimum at the origin. Again, that's the indicator from the 1D distribution that there is a repulsion. They cannot come too close to each other, and then they are most likely to be at this distance R mean. So because the potential is rotationally symmetric, we can actually also calculate the full joint distribution Pxy, and this is a plot of the distribution. So there is it's supported only over an annular region in the xy plane, xy meaning the, x and y component of the separation vector. And it's most likely to be at this, either this inner ring or this outer ring. So for the special case, when the speeds of the two particles are equal, then the minimum distance vanishes, and then we see this effective attraction that we have been seeing earlier. So the particles are most likely to be close to each other with a logarithmic divergence. So the attraction is much stronger than the underlying coupling, the underlying harmonic coupling. There is a logarithmic divergence, and it's consistent with the result that they saw for two RTPs coupled with harmonic potential. And this repulsion, again, just to re-emphasize, it comes purely due to the difference in the speeds. Now let's see what happens if we take a nonlinear coupling. In that case, we cannot solve the Langevin equation directly, but we can sort of use the same argument. But before that, we assume that this coupling is not harmonic anymore, but it's attractive everywhere, and such that the force actually vanishes as r goes to infinity. So it's a very strong coupling. So example could be just quartic coupling, that the video that we saw for. So this is the Langevin equation. We cannot solve this exactly for nonlinear cases, but if we again assume that the coupling is very strong and the activity is very large, so the time scale associated with this is very small. So then for any given θ1, θ2, this equation basically, r basically relaxes to the turning point of this equation. So this is what must be satisfied, and the minimum distance is a point of closest approach that happens to be again when θ1 is equal to θ2, which is it has to be found from the solution of this equation depending on the function f, and the maximum distance is again has to be satisfied by the maximum distance has to satisfy this equation. Okay, so let's take again the example of quartic potential. In that case, the minimum and maximum are given by this. And once again, we see that so this is a plot obtained from numerical simulations of P of r, the radial distance between two particles only. And again, we see two peaks at this r mean and r max, and they cannot come closer. And x marginal also has a qualitatively similar behavior than, similar to the harmonic case with two peaks at r mean. So, okay, so far we saw two particles, they can repel each other if their speeds are different. Now let's come to the multi-particle scenario when there are more than two particles. Let's first take the harmonic potential case, and in that case again, because everything is linear, so we look at the separation between ith and jth particles. So rij is my vector, ri minus rj, the separation between two particularly chosen particles. And that equation happens to be very similar to the two particle case, but with a renormalized coupling strength. So because each particle is interacting with all other particles, so when we are looking at a pair, the coupling strength of the pair is actually modified by the presence of the other particles in this manner. But the equation is very similar, and so we can basically use the solution of the two particle case to find the marginal distribution of any pair of particles. Distance between any pair of particles. So what happens is that each pair then maintains a minimum distance depending on their speed difference. So particle 1 maintains a particular distance with particle 2, another particular distance with particle 4, 5, etc. And this is what we saw in that video, that depending on, each pair maintains their own bound. So this is the bound. So rij has to be larger than mod of vi minus vj divided by nk, and smaller than vi plus vj by nk. And the radial distance has a similar scaling form with the same scaling function. Now same scaling function in the same structure, but then the function now depends on the ratio of r mean by r max of that pair. Same thing holds true for if we look at the x component also, similar kind of scaling form. Scaling function depends on the ratio of this r mean and r max, basically ratio of v1 minus v2 and v1 plus v2. And so it's also interesting to look at the relative orientation. So from our trivial argument, what we saw is that the minimum distance is approached when the particles are parallel. So what we do is we measure the relative orientation of two chosen particles from this combination. So here we took 6 particles and looked at the first and second particle and measured the relative orientation for a fixed r. So this is for r mean and this is for r max. And it turns out that this is really peaked very close to 0. So supporting our argument that we used to get this result. On the other hand, for Rmax, this is close to pi, so they are basically moving in the opposite direction. And they cannot go further because there is an attractive potential in the system. So finally, we have multi-particle systems with nonlinear coupling. In that case, we cannot do very much analytically, but physically you would expect kind of similar behavior, and this is what we see. So we take again quartic coupling, 6 particles, and we look at the joint distribution of let's say first and third particle x13 and y13, and it shows similar behavior to the harmonic case. So there is a excluded region in the center indicating that the repulsion really emerges in this case also, but there is a little difference here. The peak, I mean the particles are not most likely to be at the minimum or maximum separation, they are most likely to be somewhere in the middle. And this okay, so we can also look at, so basically what we see is that the phase, I mean a large region of the phase space remains inaccessible for the particles. And to see this more visually, what we looked at is that suppose we look at the joint distribution of the radial distance between first and second particle and first and third particle, I mean ij and ik, let's say. So this is the distribution. These dotted lines are the minimum and maximum for each pair, but it seems like the joint distribution is peaked in a certain region of the phase space, and the other, much of the phase space remains not accessed by the particles. And again, we look at the relative orientation between two particles for this anharmonic coupling multi-particle scenario, and we see a similar behavior. For the minimum separation, it's peaked at near theta equal to 0, so particle orientations are parallel, and for the maximum distance, it's closer to theta equal to pi. There is a little bit of spread. Sorry. Finally, so to quantify this in terms of some effective potential, what we do is that we compare it with the passive case. So for a passive case, if the particles were coupled by the same potential, then the radial distribution would be something like this. I mean, there would be a factor of temperature here, but forgetting that. So from here, we can extract an effective potential for this active case for the multi-particle case, and we expect that due to the activity, the effective potential is different for each pair, and that's what we see. So we extract the effective potential for each ij pair, and here we show this for two pairs, I think first 1, 2 and 1, 3, and we see that the effective potentials really vanish near R min and R max, they go to infinity near R min and R max, so these regions are inaccessible, and they have a minimum somewhere in the middle. So this is the minimum corresponds to this band here, and so for each pair, this is the effective potential is different. And just to give you an idea, this dashed line here is the original quartic potential. That okay, I'm going to finish early. So original quartic potential, which was much flatter. So there is a much stronger attractive coupling for each pair. This is due to activity and due to the difference between their speeds. So so we see this novel phenomenon emerging due to the speed diversity, and so far, we confined ourselves to the strongly coupled, meaning strongly active case, and we have not used any specific element of the ABP dynamics. So which is to say that the same behavior is expected also for other kinds of active dynamics like random particles or direction reversing ABP. So all the overdamped active dynamics that we know of should show similar behavior. So recently there is, 3 years ago we found work where they have studied numerically collective behavior of a set of active particles where they had this speed diversity inbuilt in the system, and they claim that this presence of the speed diversity sort of opposes cluster formation. So what we found here analytically is kind of consistent with this. We still have to look more and really look at the macroscopic scaling of this phenomenon, and in particular what happens when there is a short range interaction. So we assume a long range strong coupling, but if similar scenarios can also emerge for short range attractive coupling, or and if one can find some pattern formation or crystal formation, with this kind of scenario. That also one has to look at. And yeah, so thank you for your attention, and I'd be happy to take questions.
Okay, thank you. Questions?
Abhishek.
Like, would you this you would see in 1D also? Like, supposing in 1D you take two RTP particles
Yes.
with even harmonic attraction.
Yes.
Right? And then we know that the relative coordinates should show like repulsive, depending on parameters. So is that a similar thing? I mean,
yes. I mean, as long as the speeds are different. So if you have to, the speeds are same, then it doesn't show.
no, even same speed it should show, right? I mean, like
Repulsion.
yeah. Because we know that relative probability distribution will go from, it will look like that, and for certain parameters.
No,
like it can be either picked at the center or it can be picked at the edges, right? Wouldn't that be effective repulsion? I mean,
so this was studied by Gregory and Satya, right? Two RTPs coupled with the harmonic. 1D, two RTPs.
single, but then if you have two guys, you can,
No.
the relative will look like a single guy, right?
No, if I remember correctly, so that's what you did, right? Two particles coupled with linear potential and harmonic. So what they saw is it's picked at the origin all the time, 1D RTP.
Yeah, no, but we also had a paper with just a single RTP in a quadratic trap.
Yes, they use
this
yeah,
transition.
yeah.
But then two particles coupled by a spring, the relative will show the same thing.
No,
right?
so what I'm saying is that, so now you have this difference, so the noise becomes a little bit different, right?
Yeah.
So I think the difference, yeah, because then you will have the noise will be a three-state noise. There will be a zero. I think that zero kind of takes over. Yes.
Always get peak.
At least, I mean, that's what they found. I did not do the calculation, but they looked at linear potential and harmonic. In both cases, they saw a peak at the origin. I think this appearance of this zero makes it.
Yeah, I was just, in your summary, you mentioned short-range potentials. Is there any possibility that when the potentials aren't, sort of going all the way out to infinity with large values, you'll still get some effective repulsion?
That we don't know. That's what we would like to look at. But maybe, I mean, I was just thinking, suppose it's still strongly attractive, but there's a cutoff.
Yeah.
But
yeah.
now we have many particles and they interact within that range. So it does not seem so, I mean, so unusual to think of that it can form kind of a pattern. I mean, each
Right.
pair has, so, but we have not found anything yet.
I see. Okay. Thanks.
Like inertial term on the left hand side, does this survive? This counterintuitive thing?
Possibly. We don't know yet. We don't know it. So you mean you want to add a R double dot term, right?
Yeah. Like, is it stable to that perturbation, this counterintuitive?
Okay, for the moment, I don't know. We'll have to look at it. Yeah.
You have considered this nu I and nu j to be constant always, right?
Vi, Vj, these velocities.
Vi and Vi.
Yeah.
So what if there are some fluctuations?
Yeah, that would be interesting to study. So fluctuations, you mean that they can change over time?
They can be random or maybe fluctuate around.
So, I mean, naively, I would expect that if they are chosen from two distributions with different means, the means are still separated, probably this will survive at least in some limit. But again, I mean, we really have to, but that will probably not be very difficult to calculate.
Thank you.
So you're looking at, this completely connected model. Have you looked at something like a Rouse chain? Can you do it for?
No, not yet.
Okay. Any more questions? Okay, so if there are no more questions, thank you very much, Urna.
Thank you.
Pass to the next speaker.